Hello and welcome to Sean White's Solar and Energy Storage Podcast. In this podcast, Sean answers questions about net metering sustainability with examples from PV markets in the United States, such as Hawaii and California. Those are the big markets for energy storage, but that is changing and growing constantly. Then we're going to talk a little bit about wire sizing and how we remove the temperature adder for conduit over a rooftop in the 2017 NEC, and how wire sizing can be kind of difficult. And we'll put that into the perspective of a NABCEP PV installation professional. That's the best NABCEP certification exam that you can take, the NABCEP PVIP exam. And then we're also going to talk about solar on different faces of a roof, such as an east-facing system, and why a west-facing PV system is better than an east-facing PV system. And that's because of time of use rates. So let's jump on into the material. And remember to go to solarsean.com. Okay, and our first question says, "Hey Sean, net metering seems to be a solid financial incentive to make the grid less reliant on fossil fuels. Yet, in states like California, the utilities are worried that solar is cutting into their profits. Oh my. And they're trying to get the legislator to reduce the net metering rates, to make them worse. Do you think this will encourage more people to add batteries to their PV systems? Is there merit to net metering not being sustainable long term?" Hey Kent, that's a great question, and we have an answer for you. This is actually coming up a lot, and it just has to do with the evolution of increased PV penetration on the grid. And as more and more PV gets on the grid, of course, solar and even wind are intermittent resources, so we need to have energy storage. The good thing is, though, all of these things are going way down in price. PV is now the cheapest form of energy in the world, at less than 2 cents a kilowatt hour to produce in some places, and energy storage prices are falling faster than gravity. That's 9.8 meters per second squared. By the way, gravity on Earth. So let's look at Hawaii. Hawaii has the greatest penetration of PV on the grid, with California coming in second. That's out of the United States. Other places where there's tons of PV are like Germany and Australia, right? So in Hawaii, with that great penetration of PV, people are not even allowed to export at all during the sunny times of the days with these new systems. The older systems, however, are grandfathered in, but the newer systems, they can't export. So if they're going to be making more than they're using any significant portion of the day, then they want to get an energy storage system, otherwise known as a battery with usually an inverter attached to it. So there's a great incentive to have batteries. In the Aloha state, in California, electricity is not as expensive as it is in Hawaii. You know, Hawaii is an island, typically ran off of diesel, and there's just not a ton of people there. There's only 1 million people in Hawaii, and there's a whole bunch of islands. So there has been a lot of big battles in California. There's CALSA, California Solar and Storage Association, and they are actively lobbying in Sacramento, which is the capital of California. Things are always changing. And of course, the solar industry wants to make it better for solar, and then you have all these big pocketed utilities trying to make it better for their shareholders. So it's just part of the evolution of PV, and there will be some happy medium worked out, but that probably includes net metering getting worse. But the good thing is, though, that PV and energy storage are getting cheaper, and the idea is, hopefully, and I think probably, most definitely, PV and energy storage will get cheaper faster than the net metering policies get worse. So some of the things that they've been doing in California, which is oftentimes a model for different states because California is further along at adopting solar, is they are changing the time of use rates, and they're changing the time of use times. So before solar, the middle of the day is when everybody cranked up their air conditioner and when electricity was more scarce, and so we would have an incentive to have a time of use rate where the middle of the day would have more expensive electricity. But as more solar gets on the grid, that takes care of the middle of the day because that's when the sun is shining. And so it's the evening times now that the utilities are making the electricity more expensive, which is not so good for solar because solar doesn't work as well in the evenings as it does in the middle of the day. So then what we do is we do something called time shifting or self-consumption, where we take that PV energy, we stick it into a battery in the middle of the day, and then as you come home, you start using that energy yourself rather than exporting it onto the grid, because a lot of times there's special rules where they don't let you export battery energy to the grid, but you can use it. There's different rules everywhere, and you can't just say this is the way it is in California, because there are so many different utilities, and there's also so many different CCAs. CCAs are something that happens when an organization procures the electricity and makes the rates, but the utility, such as Pacific Gas and Electric or Southern California Edison, still works the power lines and oftentimes the billing systems. But then you have a different entity, such as Marin Clean Energy or Silicon Valley Clean Energy, that purchases the electricity and makes the rates and all that. So it's a state of constant evolution. As more solar gets onto the grid, the policies will change. If we just had regular old net metering, it would not be sustainable forever. Because if everybody had solar and nobody had a battery and everybody wanted to export at noon, and they were making more than they were using because they were making all the energy that they're going to use during the whole year, a lot of it being in the summertime in the middays, where's that going to go? If the whole grid was making more than it's using, it just doesn't work. So it's just evolution, solar evolution on the grid. Okay, this next question comes from Ondine. Ondine says, the training materials that you have seem to be very helpful for the PV installation professional exam, that's a NAPCEP exam, preparation, as well as improving my general knowledge of everything solar. I'm having a little trouble understanding how to do the calculation with source and output conductors and conduits. That would be PV source circuits and PV output circuits. With respect to the conduits on the roof that are exposed to sunlight. Obviously, the ampacity drops as the temperature goes up, and there are correction factors that calculate a minimum conductor size for any situation. How would one know the actual temperature adder to cross-reference with table 310.15b2a? That's the 2017 NEC. Would the PVIP exam just tell you what the ambient temperature is? Obviously, EMT, 2 inches high on a black rooftop in Phoenix, Arizona, would need a different correction factor than a 6-inch high EMT in Anchorage, Alaska on a white roof. I just don't want to miss a question on the test due to plugging in an incorrect number. Another question that I have is about table 310.15b3a. Why is a grounding or bonding conductor not counted? I understand that these should not add any heat unless there is a fault, but these wires still take up space inside of conduit, which should in turn add heat. What about less than 3 current carrying conductors? Do you just not use this table? Okay, Ondine, let's answer your question. First of all, you do not have to use an adder for temperature for conduit and sunlight anymore, unless you're using the 2014 NEC or earlier, which they're still doing in some places, but most places have turned over to the 2017 National Electrical Code, and we don't have to have a temperature adder, well, unless you're 7/8 of an inch over the roof or less, but nobody puts their conduit that low over the roof because debris and leaves and all that kind of stuff would get stuck under the conduit. So you want to have that conduit higher for multiple reasons, the debris, and so you don't have to add that adder, that 33 degrees Celsius for 7/8 of an inch or less. And so that's all you have to deal with if you're not using the 2014 National Electrical Code, if you're using something newer like 2017, 2020, 2023, 2026, 2029. I know we're kind of getting into the future there, but hey, let's future-proof this. But anyway, NAPCEP probably is not going to trick you on some question like that because they're not into tricking you on different versions of the National Electrical Code. In fact, one time somebody told me on a NAPCEP test that they had something that was for the previous version of the code, obviously, that really didn't even work with the way that the question was written. So don't worry. No, those NAPCEP test writers are not sitting there going, let's try to trick these people by using the most recent version of the code and making some tricky question. And also, there's not a whole lot to these NAPCEP exams as far as wire sizing goes. Woo! But if they do give you a question and it had something to do with temperatures, they would give you the temperature. I mean, they have to give it to you. What are you going to do? Take a guess? Memorize all the temperatures for every place in the United States? Nope, they're going to give you the temperature. And if you need to get the temperature yourself and you're not taking a test, there's a website that you can go to, and it's Solar ABCS, that's solarabcs.org/permitting, and you can find out all the temperatures there. And for the high temperature, it's recommended to use the 2% high temperature, not the 0.4%. And the 2% high temperature is a lower temperature than the 0.4% high temperature. And that's okay to do, even according to those people pushing copper. That's the Copper Development Association says it's okay to use the 2% high temperature. You can read all about that at Solar ABCs. And that was put together by our good friend Bill Brooks. Yeah, Bill. Now, for your 310.15 B3A question, and that's the way that they label it in the 2017 NEC. If you wanted to go to the 2020 NEC, that's 310.15 C1. And anyway, let's talk about what that is. That's just how many conductors are in a conduit. And this isn't for physically how many conductors are taking up space as far as dissipating heat, but I can see what you say. If there's less room for air because you have more conductors in there, you can make an argument. But what this table is really about is these conductors that are generating heat. That's what this is all about. This table, 310.15 B3A, is about greater than 3 current carrying conductors in conduit. And when you have more than 3 current carrying conductors in conduit, you have to look at this table and then you have to derate for heat. So if you had 4 current carrying conductors in conduit, not including grounds or balanced neutrals, then you would have a 0.8 derating. It says 80% in that table. And that's an example. Okay, so now if you want to figure out how many conductors fit in your conduit, you do that somewhere else. And so you can do that in Chapter 9, Tables 1, 4, and 5. And that pretty much does not change throughout the different versions of the NEC, even back to Egyptian times, right? They still used Chapter 9, Tables 1, 4, and 5, right? King Tut. Unfortunately, we can't see that because the Library of Alexandria was burned down and we can't see that earlier version of the National Electrical Code. That's a joke, by the way, because the first National Electrical Code was penned in 1897. So like if you wanted to just physically figure out how many conductors fit in conduit, you have Chapter 9, Tables 1, 4, and 5. Or if all of your conductors are the same size, it's much easier to go to Informational Annex C. So wire sizing is very complex and most people don't understand it. Even if you get the top experts in the world sitting around a table talking about wire sizing in NEC, they're likely to disagree with each other, and 99% of the time, they'll have the same size wire, but 1% of the time, those top experts in the world will even disagree on the wire size. When people don't do wire sizing exactly by the book, almost always they end up with a larger conductor than they need, which is also just a good idea because a larger conductor works better and it's safer. So I do cover wire sizing in my advanced 40-hour PV course at HeatSpring in detail and my 30-hour course on HeatSpring. Another place that I cover wire sizing with good examples are my books PV and the NEC, which I wrote with Bill Brooks, and my other book, PV Engineering and Installation. Both of those books have complete chapters on wire sizing. Yep, wire sizing. That is some exciting stuff. And for our next question, we have Dennis. And Dennis wants to know, says, hey, Sean, let's say you have a house that is north-south facing with an A-frame roof. I've seen many of these in Boulder, that's in Colorado, that have their systems on the east-facing side. Because of the peak hour charges and time of use, wouldn't it make more sense to have these systems facing the west side, right? And that's totally right. Yes, if you have an east-west facing roof, that would be with an east-west facing roof, not a north-south facing roof. But anyway, if you had a roof facing east and west, I always recommend going west if you can, unless there's a big tree in front of it, because if you don't even have time of use rates right now, you might sometime in the future. And that afternoon energy is just more valuable. That's when people come home from work and some people are still at work. Oh, do people still work at an office? Maybe they just work from home. But anyway, that's just the big time for energy usage. The sun's been shining all day. The air conditioners are cranked up. People are at the store. People are in all the buildings. Stuff's just turned on in the afternoons. And that's when it happens. You've probably heard of the duck curve. The duck curve is what happens when there's a lot of solar on the grid. It reduces the need for extra electricity in the middle of the day when the sun is shining, and then you have this big demand as the sun starts to set. And that's the duck's head, and that's in the afternoon, and that's when the sun is to the west. And so that's why having your PV system facing west is just better. than facing east. However, some people might try to sell a system and argue that, well, if the sun is in the east, the PV is a little bit cooler, so you can make more energy in the morning because it's cooler, because your voltage will be a little bit higher. And that's correct. But I just think that those time of use rates that you have now or that you will have in the future are just going to make a bigger difference. Plus, it's just helping out the grid more to be facing to the west because people like to use solar more often in the afternoons. That's not to say that south facing is not the best way to face something, especially if you're just looking at what's your maximum energy production. And then to overcome some of these things by facing the wrong direction, you can also use energy storage. And when you use energy storage, we call that time shifting and self-consumption, as we already just mentioned with that last question. And so what we can do is take that energy that we made during the day, and then you get home, you start using stuff, and instead of importing from the grid, you're just using just the right amount from your battery. Everything's controlled by electronics. So you're not exporting to the grid, but you're using that battery. In some places, they might even allow you to export to the grid, but one of the things that they're afraid of is they call them brown electrons. So they don't want you taking that dirty grid energy and putting that dirty energy in the battery when electricity is cheap with a time of use rate, and then exporting it back out to the grid when the electricity is more expensive. They want you to use that green, clean solar energy from your battery for your own loads. They don't want that going out to the grid. But there's like kind of almost infinity different utility rate schedules, or getting close to it. I know I'm exaggerating. So you have to just figure out for yourself what's going to be the best deal. But also, batteries are not totally cheap yet. And there's a loss in efficiency with batteries, with any kind of battery. Lead acid batteries, the loss of efficiency, you might be losing 30%. So that would be 70% round trip efficiency. And with lithium batteries, maybe you're at 90 to 95% efficient round trip for taking electricity, sticking it in a battery, and then back out to electricity again. That's your round trip efficiency. One of the poor things about hydrogen storage, speaking of round trip efficiency, is with hydrogen, it's about 35%. So that means you take electricity, you turn it into hydrogen, and you turn it back into electricity again. You're losing 65% of that energy just in all that conversion. And that's why lithium batteries, in my opinion, beat hydrogen. But hydrogen just sounds so cool, right? Hydrogen. All right. Thanks for listening to Sean White's Solar and Energy Storage Podcast, where you can find out everything under the sun about everything solar and storage and a couple more things. And to find out more, go to Solar, SEAN, that's SolarSean.com.